Hi Shika, good evening. Okay. Okay, let's wait at least 1 minute, then we'll start. So today I'm thinking I'll discuss some important topics from statistical mechanics, actually, which will be important for your GATE exam. Like some basic topics like concept of microstates, ensemble, different kinds of ensemble like this, partition function. Link of this session means recording link. Okay, I'll send you the recording link, no problem. Yeah, sure, Sika, no problem. I'll send you the recording link by today or tomorrow. I'll send you the recording link. Okay, so let's start gradually. Let me just share my screen. Okay, so let's start. So today we'll discuss statistical mechanics. Okay, just checking, am I audible properly? Just can anyone let me know? Okay, thanks. Okay, so statistical mechanics is the basis of statistical mechanics is to basically understand the microscopic basis of different macroscopic properties. Okay, so statistical mechanics actually from microscopic basis of different macroscopic quantities. Macroscopic properties. Now different macroscopic properties mean it could be like average energy or the properties of phase transition, concept of entropy, so all kinds of properties. So if the microscopic properties actually are thermodynamical properties like pressure, volume, energy, entropy, internal energy, enthalpy, like this, then we call this statistical mechanics as statistical thermodynamics. Okay, now now basically what do you mean by thermodynamic system? Thermodynamic system. So thermodynamic system means the total number of particle in tends to infinity, or a very large number of particle, a system where very large number of particles is present, the volume of the system tends to infinity, but the ratio n by v, which is the number density, let's call it rho, which is finite. Okay, so the thermodynamic system means the total number of particles tends to infinity, the volume of the system tends to infinity. That means very large number of particles is present and the volume is also very large, but the number by volume, which is the number density, is finite. Okay, now the important concept in statistical mechanics is concept of macrostate, right? So macrostate means a thermodynamical state where the different macroscopic properties are mentioned. So macrostate means a thermodynamical state where different macroscopic quantities are mentioned. So that means it can be like N, V and T. Okay, so a system or a macrostate where the total number of particles N, total volume of the system V and the temperature of our system is mentioned. So these are all macroscopic properties, like properties of macroscopic system N, V and T. So a large system or a thermodynamical system where the number of particles in volume of the system and the temperature is mentioned, so we call the macrostate of that thermodynamical system is NVT, or macrostate is defined by NVT like this. It can be NVE also, like thermodynamical state where the number of particles, volume of the system and energy is fixed or is mentioned. So that thermodynamical state or macrostate is defined by NVE like this. So these are all macrostates. Okay. Now the important point is instantaneous configurations or microstates. Configuration, instantaneous configurations. So let's say we have a macrostate which is defined by N, V and E. So in this macrostate, the total number of particles, the volume of the system and the energy is conserved or is mentioned properly, explicitly. Okay. Now let's say there are 3 particles. Let's say n equal to 3 and energy is some, let's say 3 epsilon. Okay, so epsilon is the unit of energy, let's say. So total number of particle of this macrostate is 3 and the energy is 3 epsilon, let's say. Now with these configurations like n equal to 3 and E equal to 3 epsilon, there are many possibilities, like so the particles, the 3 particles can arrange in different energy levels, right? So these 3 particles can arrange in different energy levels. Now these particles can be both be distinguishable or indistinguishable. So I'll come to that later. It can be indistinguishable particle. Indistinguishable means we cannot distinguish between particle A and particle B, or particle B or particle C, or it can be distinguishable. Okay, so there are the energy labels, let's say like this. This is 0, this is epsilon, this is 2 epsilon, this is 3 epsilon. Okay, so these are the energy levels. There are many energy levels here. So our system's particle number is 3, and the total energy is 3 epsilon. So the possibilities here are, let's say, the configuration number 1. So one particle, let's say one particle is here in energy level 0, another particle is energy level, let's say, epsilon, and another particle is energy level 2 epsilon. Let's consider this configuration. So this is actually an instantaneous configuration. Okay, so here the total energy of this configuration is how much? 3 epsilon, because the one particle is in epsilon and another particle is in 2 epsilon. So total energy is 3 epsilon. So these satisfy our macrostate condition. So this is actually instantaneous configuration. Now if the particles are indistinguishable, let's say this is particle A, this is particle B, this is particle C. So if, let's say, if A, B, C particles are indistinguishable, that means we cannot distinguish between particle A, particle B, or particle B, particle C, or particle A, particle C, then this configuration is the only possibility, right? But if the particles are distinguishable, then it does matter that where particle A is present and where particle B is present and where particle C is present, because we can now distinguish between the particle A, B, C. That's why this is not the only configurations possible. There are many configurations possible. Under this configuration there are many states possible, like this is one state, second possibility is 0 epsilon, 2 epsilon, 3 epsilon. Let's say particle B is here, particle A is here, particle C is here. Now for this configuration the total energy is also 3 epsilon, but here the particle B is in 0 state, in here the particle A is in 0 state. So if the particles are distinguishable, then these two are two different states under one instantaneous configuration. So like this, so particle C can be here, particle B can be here, particle A can be here. So all these states are possible. So all these different states are called microstates. Okay, so macrostate means here the NVE is defined for a thermodynamical system, so that is our macrostate. Now under this macrostate we define, let's say, n equal to 3 and E equal to 3 epsilon. So this configuration is actually one instantaneous configuration. Okay, now under this instantaneous configuration, if the particles are distinguishable, then all these possibilities are there, like so under this instantaneous configuration, this one instantaneous configuration, all these states are microstates. Okay, so under this configuration there are six possible microstates. You can just draw 6 possible microstate, or another way to count the possible microstates under any instantaneous configuration is this. Just you can remember that. Okay, so let's say our instantaneous configuration is this: 0 epsilon, 2 epsilon, 3 epsilon. Now one particle is in energy level 0, one particle is in energy level epsilon, and one particle is in energy level 2 epsilon. So this is our instantaneous configuration. Now let's say the particles are distinguishable, because if the particle are indistinguishable, then this is the only possibility, right? But if the particles are distinguishable, then there are many possible microstates under this configuration. So number of microstates will be the total the n factorial, which is the total number of particle divided by the, let's say in 0 energy level there is one particle, that means 1 factorial. In epsilon energy level there is one particle, that means 1 factorial. In 2 epsilon energy level there is one particle, which is 1 factorial. But and rest are 0, no other particles are there. So in other energy levels there is 0 particle, so that means 0 factorial. Okay, so here n equal to 3, so 3 factorial divided by 1 factorial, 1 factor, that means all are 1. So 3 factorial means 6. So that's why under this instantaneous configuration, there are 6 possible microstates. Okay, you can count microstates like that. Let's consider another instantaneous configuration. Let's say the energy level is like this: 0 epsilon, 2 epsilon, 3 epsilon, 4 epsilon, like this. N equal to 3 and total energy is 3 epsilon, right? Let's say there are 2 particles is in energy level 0 and another particle is in energy level 3 epsilon. Okay, so this is another possibility, right? So this is another instantaneous configuration. Under the microstate NVE. So here in this case is also the total energy is 3 epsilon. Now what would be the total number of microstates if the particles are distinguishable? So if the particles are distinguishable, then the number of microstates under this instantaneous configuration will be, the total number of particles is 3, that means 3 factorial. Now in 0 energy level there is 2 particles, right? So 2 particles can arrange themselves like 2 factorial. In epsilon energy level there is 0 particle, 2 epsilon then there is no other particle, and 3 epsilon energy level there is 1 particle, that means 1 factorial, and there is no other particles in 4 epsilon, 5 epsilon, like this, so 0 factorial. Okay, so that will be the 3 factorial divided by 2 factorial, right? So 6 divided by 2, that means 3. So under this instantaneous configuration there are 3 possible microstates. Okay, now what will be the 3 possible microstates? So one possibility is particle A, B is in energy level 0 and C is in energy level 3 epsilon. Particle B, C is in energy level 0 and A is in energy level 3 epsilon. Particle A, C are in energy level 0 and B is in energy level 3 epsilon. So these are only 3 possibilities under this instantaneous configuration. So these are 3 microstates. Like this. Okay, now under the macrostate n equal to 3 and E equal to 3 epsilon, there is another possibilities, another instantaneous configuration, which is all 3 particles are in energy level epsilon. In this case also the total energy is 3 epsilon. So this is another instantaneous configuration. Okay, now what will be the number of microstates under this configuration? So number of microstates total number of particles is 3 factorial, and in 0 there is 0 factorial, then in epsilon there are 3 particles, so 3 factorial, then all other case 0 factorial. Okay, so that means 3 factorial by 3 factorial, which is 1. So this is the only possibility. So the number of microstates under this configuration is 1. Okay, so by this way you can count the total number of microstates under any instantaneous configuration. Okay, let's say you have given total number of particles is 2 or 4, and the total energy is 2 epsilon, or let's say 4 epsilon. Then count the possible instantaneous configurations and count the possible microstates under each instantaneous configuration. You can count like this way. Okay, now if the highest number of microstates under the instantaneous configuration is called the most dominating configuration. Okay, that will dominate most. Okay, so let's just talk about ensembles. Okay. So ensembles, so there are mainly or importantly there are 3 kinds of ensemble. There are many kinds of ensemble are possible, but only 3 kind of ensemble is there. So which will be the most important. First one is the, let's say, microcanonical ensemble. Microcanonical ensemble. Ensemble means a collection of systems. Collection of systems, which is called ensemble. Microcanonical ensemble means the total number of particles in volume of the system V and energy is conserved. Okay, this is called microcanonical ensemble. Second one is canonical ensemble. Where the number of particles in volume of the system V and temperature is constant. Okay, so that means, let's say, ensemble is a collection of systems. So this is, let's say, considered an ensemble, and here the many systems are there. Okay. Now for this ensemble, the total NVT is constant, right? So NVT is constant means between these systems energy is fluctuating. So by energy is fluctuating, so that's why the temperature of a system is constant. Okay, so this is canonical ensemble. Third one is actually grand canonical ensemble. Where the chemical potential mu and the volume of the system V and temperature of the system is constant, which is mu Vt. Here between these systems the number of particles will also vary or will also fluctuate. That's why here the chemical potential is kept constant, but number of particles can vary. Okay, so these are the 3 main ensemble. Now most important is one is the canonical ensemble, where the number of particles n is constant, the volume of the system is constant, and the temperature of the system is constant. Okay, now let's talk about canonical ensemble. So okay, so first I'll talk about the partition function. Okay. I did not derive anything, so let me just talk. Okay, so let's say there is a molecule or particle where there are different energy levels are there. Okay, 0, like epsilon, 2 epsilon, 3 epsilon, like this different energy levels are there. Now at a finite temperature, so particles actually can arrange in different energy levels. So let's say there are 3 particles in energy level 0, 1 particle is in energy level epsilon, 1 particle is energy level 2 epsilon, like this. So depending upon the temperature, so at low temperature, let's say 0 temperature, so all the particles are in energy level 0. But if we increase the temperature, then the particles can actually excite and particles can actually arrange in different possible energy levels. So depending upon the temperature, there are different kinds of distributions are possible. Okay, now how these particles are distributed or arranged in different energy levels, this can be defined by partition function, like how these particles are partitioned in different energy levels. That's why the name is partition function. Okay, so let's say there are n1 number of particles is in energy level 0, n2 number of particles is in energy level epsilon, like this. So all these arrangements can be defined by the partition function. So in canonical ensemble, the partition function is defined by, let's say, z. So z will be equal to so z will be equal to sum of all energy levels. Okay, so let's say I equal to 1 to infinity, all possible energy levels, then exponential minus epsilon I divided by kBt. Okay, epsilon I is the energy of the ith energy level. Okay, this is ith energy level, and sum is going from all possible energy level, I equal to 1 to infinity, and exponential epsilon I divided by kBt. Kb is the Boltzmann constant, and T is the temperature. There is another name also, which is beta, inverse temperature, which is 1 upon kBt. Okay, so this is the expression for the partition function in canonical ensemble. Now let's say in different questions you can see, let's say there are 2 possible energy states, 2 state system, only 2 energy levels are possible. Let's say this is epsilon 1, this is epsilon 2. Okay, now in the question we are asked that now what is the probability of finding the particle is in energy level epsilon 2. Okay, just a second. So let's say what is the probability of finding the particle in energy level epsilon 2. So we can find that the probability, the expression for the probability will be just exponential e to the power minus epsilon 2 divided by kBt. That means the energy of that state divided by kBt divided by the sum of all possible energy levels, then minus epsilon I divided by kBt. Okay, so this is the expression for finding the probability of finding a particle in a particular energy state. Now you can simplify this, so P probability will be just minus epsilon I, let's say Pi, probability of finding a particle in energy state I. So Pi will be epsilon I divided by kBT divided by total number. This expression is actually the partition function by Z. Okay, so this is the expression to finding the probability. Now let's say in the question you were asked that to find the probability ratio, like a ratio between the P1 and P2. So P1 is the probability of finding the particle is in energy state epsilon 1, and P2 is the probability of finding the particle is in energy state epsilon 2. So you have to find that P1 divided by P2. Okay, so P1, you know P1 equal to exponential minus epsilon 1 divided by kBT divided by Z, and P2 is exponential minus epsilon 2 divided by kBT divided by Z. Okay, so Z will cancel, so exponential minus epsilon 1 divided by kBT divided by exponential minus epsilon 2 divided by kBT. kBT, then exponential epsilon 2 divided by kBT. Okay, so exponential epsilon 2 minus epsilon 1 divided by kBT. So this is the expression for the P1 divided by P2. So epsilon 2 minus epsilon, we have to know just what is the temperature value. We know the kB value. We have to just know the epsilon 2 minus epsilon 1. So epsilon 2 minus epsilon 1 is the energy difference. So if we know the energy difference, we can calculate the probability ratio P1 divided by P2. Okay. Okay, so this is the basic concepts of partition function. Now from the partition function, from this expression Z equal to sum over I equal to 1 to infinity exponential minus epsilon I divided by kBT. Okay, so this is the expression of partition function in canonical ensemble. Now from this expression we can just derive different thermodynamic properties or thermodynamic quantities like average energy, pressure, volume, entropy, Helmholtz free energy, heat capacity, Cp, Gibbs free energy. All these thermodynamic quantities can be derivable from the expression of the partition function Z. Okay. Now what is the expression of energy? So you should remember this. The expression of average energy is sum of epsilon I in I, right? So this is the expression of average energy. So let's say Ni particles is in energy level epsilon I. So average particle will be just I equal to 1 to infinity sum of epsilon I Ni divided by total number of n. So if you just derive the expression of the average energy, so it will be just kB t square del ln z by del t constant n constant v. Okay, so this is the expression to compute the average energy. kB t square del ln z, here z is the single molecule partition function and T is the temperature, Kb is the Boltzmann constant. So if you know the partition function Z, you can compute the average energy with this equation. Okay, now Helmholtz free energy you can also compute. A equal to minus kBT ln Z. Okay, this is the expression to compute the Helmholtz free energy. So this is Helmholtz free energy. Okay, now for n particle, it will be n minus n kBT, like this. Now to calculate, so these expressions are considered, the particles are distinguishable. Now for indistinguishable particle, you have to just here you have to just define Z n particle partition function. Okay, so all these expressions are for distinguishable particle. Now for indistinguishable particle, the n particle partition function would be Zs to the power n divided by n factorial. Okay, so Zs is the single particle partition function. So for n particle partition function where the particles are indistinguishable, which will be the Zs to the power n divided by n factorial. Okay, now to compute the translational partition function. Okay, so there are different kinds of partition function. So translational partition function means partition function for corresponding to the translational degrees of freedom. Okay, so this expression actually can be derived by considering the particle in a box problem. I am not deriving the expression. So translational partition function Z will be V divided by lambda q. Just a second. Okay, V divided by lambda cube. The V is the volume of the system, lambda is the thermal de Broglie wavelength or de Broglie wavelength. Okay, so this is the expression for translational partition function. Lambda or thermal de Broglie wavelength is h divided by root over of 2 pi m kBt. So this is important. Thermal de Broglie wavelength, h is the Planck constant, and m is the mass of the particle, kb is the Boltzmann constant, T is the temperature. So thermal de Broglie wavelength is proportional to 1 over root T or proportional to 1 over root m. So if the temperature is high, if T is high, then the thermal de Broglie wavelength is low. Okay. So okay, so another thing is that vibrational partition function for, let's say, harmonic oscillators. Vibrational partition function for simple harmonic oscillators. So we know the energy expression for the quantum mechanical energy expression for simple harmonic oscillator is n plus half h nu or n plus half h bar omega, right? So the partition function will be just Z sum over all possible energy level, that means 0 to infinity. Okay, then minus En divided by kBt, right? So n equal to 0 to infinity exponential minus n plus half h bar omega divided by kBt. Okay, so this is the general expression of the vibrational partition function. Now you can just compute that. So e to the power minus half h bar omega will be common, so e to the power minus half h bar omega divided by kBt you can take common, then n equal to 0 to infinity exponential minus n h bar omega by kBt, right? So now for this case you can just exponential minus, so for first case it will be 1 plus exponential minus h bar omega by kBt plus exponential minus 2 h bar omega by kBt, like this. So this, if you just take the h so exponential minus h bar omega by kBt equal to x, so it will be 1 plus x square, like this. So the general expression for this infinity series is 1 by 1 minus x, right? So the vibrational partition function for simple harmonic oscillator will be exponential minus half h bar omega by kBt times 1 divided by 1 minus x. X means exponential minus h bar omega by kBt, right? So this is the full expression of vibrational partition function for simple harmonic oscillators. Okay, now the one important topic is the heat capacity. So heat capacity is the amount of heat required to raise the temperature of a given substance by unity, right? Heat capacity is amount of heat required to raise the temperature of a given substance by unity. Okay, so there are many types of heat capacities like Cp, Cv, constant pressure heat capacity, constant volume heat capacity. So Cv you can compute by del U del Tv. That means by just taking the derivative of internal energy U with respect to temperature, you can get the Cv. Here U is the internal energy. And Cp you can compute by del H del Pt. That means by taking derivative with respect to pressure of enthalpy. H is the enthalpy here. Okay. Now for heat capacity of solid case, often you can just you can see that there is a plot where heat capacity, lattice heat capacity of solid with respect to temperature. Okay, so the plot is generally look like this. So this is actually 3R. So at high temperature, at very high temperature, the heat capacity of solid corresponds to 3R. If there are n particles, then the heat capacity will be 3R. Oh, sorry, 3 degrees of freedom system, so heat capacity will be 3R at high temperature. But heat capacity generally decreases if you decrease the temperature. If you just decrease temperature, the heat capacity is actually decreasing. Now at temperature equal to 0, so 0 temperature, heat capacity tends to 0. Okay, you can see that here. So this is the third law of thermodynamics. Like at T tends to 0, like temperature equal to 0, the heat capacity is also 0. So this is the third law of thermodynamics. Now at low temperature, at this region, this is the heat capacity actually increasing or actually varies with T cube. heat capacity, this region, along at this region heat capacity varies with T cube, like this. So this we known, and this we call the d by T cube law, d by T cube law. So this is actually important. So at low temperature heat capacity varies with T to the power cube. This is the heat capacity of solid. Okay. Now there are also rotational partition function. So rotational partition function means so in the if you have to just define the energy. So energy corresponding to the rigid rotor, the quantum mechanical energy expression for the rigid rotor is J into J plus 1 h bar square divided by 8 m r square pi square. So J into J plus 1 h square by 8 pi square I. Okay, so this is the quantum mechanical expression of rotational partition function. So J is the rotational quantum number, and so J can vary from 0 to infinity, 0, 1, 2, 3, and H is the Planck constant, I is the moment of inertia. And now the partition function is Z equal to just sum over all possible energy levels, I equal to 0 to infinity, exponential minus epsilon I or Ej, let's say it is J, divided by kBt. Okay. Now from the rotational partition function, the important point is what is the allowed values of quantum number J for ortho hydrogen and para hydrogen. You often see this question. Okay, ortho hydrogen and para hydrogen. What is the allowed values of rotational quantum number? So ortho hydrogen means where the nuclear spin of hydrogen atom is symmetric with respect to interchange of two hydrogen atom. Let's say this is one hydrogen atom, this is another hydrogen atom. So if the nuclear spin is symmetric with respect to interchange, let's say this nuclear spin is rotating is along this direction. Okay, now if we interchange these two hydrogen atom, the nuclear spin will be symmetric, right? So that's why we call this ortho hydrogen. Here the nuclear spin is symmetric with respect to the interchange of two hydrogen atom. Now for para hydrogen case, if we just alter or interchange these two hydrogen atom, the nuclear spin will be anti-symmetric to each other. That means one is in this direction, let's say another is in this direction. So here the nuclear spin is anti-symmetric. Okay, now you know, according to the Pauli exclusion principle, you know the total wave function of any molecule has to be anti-symmetric, right? So according to Pauli exclusion principle, the total wave function has to be anti-symmetric. Okay, now for ortho hydrogen case, nuclear spin is symmetric. Nuclear spin wave function is symmetric, right? Now the rotational wave function. So here the total wave function is a product of nuclear wave function like nuclear spin wave function times the rotational wave function. Okay, so here nuclear wave function is symmetric. Now so the total wave function has to be antisymmetric. That means the rotational part has to be antisymmetric in the orthohydrogen case, right? It has to be antisymmetric. Now for the rotational partition function, the rotational wave function, the antisymmetric wave function means the odd quantum number. Okay, so that means J equal to 1, 3, 5 like this. So odd quantum number corresponds to the antisymmetric wave function. So for orthohydrogen case, the rotational partition function has the contribution from the odd quantum number J equal to 1, 3, 5 like this. And for parahydrogen case, the total wave function is actually the spin wave function times the rotational wave function. Here the spin part is antisymmetric, so total wave function has to be antisymmetric. That means the rotational part has to be symmetric, right? Because antisymmetric times symmetric will be antisymmetric, but if antisymmetric times antisymmetric will be symmetric like this, it has to be symmetric. And so the even quantum number J equal to 0, 2, 4, 6, the even quantum number corresponds to the symmetric. So parahydrogen case, the partition function has the contribution from the even quantum number like 0, 2, 4, 6, etc. For orthohydrogen case, it has the contribution from the odd quantum number, that means 1, 3, 5 like this. Okay, so this is actually important. Okay, and the last thing is actually for degeneracy. Let's say if you have a system of two possible energy states, but let's say for this is epsilon 1, let's say epsilon 2. Now for epsilon 2, let's say that there is a degeneracy. So degeneracy is, let's say, 2. That means for epsilon 2 energy state, there are two possible energy level of same energy. The degeneracy means the number of possible energy levels of same energy. So in epsilon 2, degeneracy is 2 means there are two possible energy levels are there. Now to compute the partition function for this case, so Z will be, the expression will be similar, sum over total number of possible energy states I equal to 1 to infinity Gi exponential minus epsilon I divided by kBt. Okay, here I is actually the energy state, epsilon I is the energy of that state. Now Gi is the degeneracy. So let's say for this case where there is only one possible energy state is epsilon 1 and two possible energy levels is epsilon 2. Okay, so here Z will be G1 means 1, so 1 times exponential minus epsilon 1 divided by kBt plus G2 means there are two possible energy levels in epsilon 2, so that's why we have to multiply by 2 times epsilon exponential minus epsilon 2 by kBt. So the partition function for this system will look like this. Okay, so this is the general expression for degeneration. Gi times exponential minus epsilon I by kBt. Gi is the degeneracy corresponding to that particular energy state. Okay, so these are the basics of stat mech, I think. Okay, so any doubts or in the next class also we'll discuss some more topics like from stat mech or thermodynamics.
Sir,
Yeah.
sir, please explain the third law of thermodynamics.
Okay.
I studied about the entropy only. You say the heat capacity is zero.
Yeah. So third law of thermodynamics is basically that if the temperature goes to zero, then the heat capacity is also zero. That means entropy is also zero. That means if the at zero temperature all the particles are still like it is considered that they don't vibrate. So that's why we consider the entropy is also entropy zero. But there is exactly entropy don't vanish at zero temperature. There is a residual entropy also, like because at zero temperature atoms are still vibrating, so there will be residual entropy at zero temperature. Okay, just let me just check. Yeah, so basically third law says at temperature equal to zero, for it the important point is for pure and crystalline solid, the entropy vanishes, entropy equal to zero, the absolute entropy. So absolute entropy equal to zero at T equal to zero for pure and crystalline solid. Now if the entropy is zero for pure and crystalline solid, that means all the atoms in the solids are not vibrating. Okay, they are still at zero temperature, they are stationary, they are not vibrating. So that's why the heat capacity is also zero. But for not pure solid, like there will be defects, or at zero temperature the atoms will be vibrating, so that there will be residual entropy depending upon the condition. But yeah, regarding the heat capacity plot for pure and crystalline solid, the heat capacity plot will look like this. At zero temperature the heat capacity is zero, then at high temperature the heat capacity is 3R, and at low temperature, like in this region, the heat capacity vanishes with T to the power cube. Okay, so this zero is actually for pure and perfectly crystalline solid. That means atoms are not vibrating in that case. So that's why the entropy is also zero, absolute entropy, and heat capacity is also zero. Clear?
Yes, sir.
Heat capacity zero means if you just increase temperature, okay, if you just increase the heat, if you just give heat, the temperature is not increasing. So if the atoms are still not vibrating, then there is no meaning of giving heat. So that's why. Okay, so any other doubts? Okay, so next class I think we'll be discussing some topics from equilibrium or thermodynamics. Okay. Say, are these sessions helpful for you guys? I don't know. Is it helpful? Okay. Okay, great. Okay, thanks. So today I'll just signing up, and see you soon see you meet in the next week. Okay, bye. Bye, thanks for joining. I'm just signing off.